So this is the next set of questions on the practice exam A. So we have this joint probability table. We're going to call being older than 55 event O. So yes, they're older than 55 would be event O. Not being older than 55, then we can think about as O complement. We then also have wanting marijuana nationally legalized, being yes or no, where yes, if they do, we'll call that LM. No, we would call that LM complement. So we're given quite a bit of the information here. I guess I'm not sure why this 0 was left off here, but just to make that look a little nicer. If you want to find this missing value of x, remember what we said is that if we take these top 4 left cells, they all represent intersections. We went through in more depth why we can do this in lecture, but we said the way we get these totals is actually adding down the columns or across the rows. We think about why, if I'm older than 55 and I want marijuana legalized, and then I take the group of people who are older than 55 that don't, when I add those together, that's just everybody who's over 55, and that's why it gives me the total. So if I don't know what x is here, I could solve for it a couple different ways. I think adding across the rows is the easiest, right? So all I'm going to do there is take 0.52 plus x is equal to 0.57, right? If I add these two together, 0.52 plus x, that should equal that total of 0.57. From here, it's really just a little bit of algebra. So we subtract 0.52 from each side, and we end up getting that x is equal to 0.23. So that one should be pretty easy. Hopefully a lot of people get that one correct on the exam. I could have also added down the columns. Notice 0.11 plus 0.23 also gets me 0.34. So it's also a way I could check to make sure I didn't make a math error, is add down the column to find x, add across the row to find x, and hopefully if I do things correctly, I'll find the same value. So the next question we have is, what's the probability that someone is 55 or older and they favor the support of legalizing marijuana? So here, I would write down what we want to find. So the probability that someone is older than 55, which is event O. And that it helps you, you could just write these out. So older than 55, and which if we wanted to put in an actual set sign there, okay, let me delete this so I can kind of show you what that looks like. Remember we said the and symbol is, where is this? Why am I blanking on where it's at? Here we go. The and symbol is this kind of upside down U. So older than 55 and they want marijuana legalized. So we have kind of this intersection. Now remember, these top 4 left cells all represent intersections. So all we have to do to solve this one is, are they older than 55? Yes. Do they want marijuana legalized? Yes. And so that should be, oh wait, did I read this wrong? Oh, yeah, I did. They do not favor, right? So they don't want marijuana legalized. So we actually go, they're older than 55 and do not want marijuana legalized. So that should just be in that cell there, because that represents the intersection of those two things, or 0.11. So the next question we have is, given that a person believes in in the legalization of marijuana, so we'll go, the given is what comes after that vertical line when we're writing a conditional probability. So what we were given is they want marijuana legalized. Once again, I could have just written this as like LM, right, the event LM, but if it makes it easier, I can write out the actual word. So what is so given that, what's the probability that a person is over 55? So I've got this conditional probability, okay? So if I go to my formula sheet, and actually, oh, wrong one. So I go to my formula sheet, I go up here, and I remember, okay, if I want a conditional probability, that's just the intersection of the two events divided by whatever I'm conditioning on. So if I write this out, I want older than 55 and marijuana legalized, and I want to divide that by the probability of what I conditioned on, so that's what's to the right of that vertical line, so that's wanting marijuana legalized. All right? Now if I'm writing this out and kind of how I was calling those events, we could think about this as older than 55 and marijuana legalized divided by the probability of wanting marijuana legalized, right? It doesn't matter if I reuse the words or just the kind of real shorthand. So what's the probability that someone is older than 55 and wants marijuana legalized? So older than 55 and want marijuana legalized. So that's 0.14 divided by the probability they want marijuana legalized. So wanting marijuana legalized all the way down to the total. Divide that by 0.66. So if I enter that into my calculator, I should get about 0.21 if I round it to the second decimal point. Okay. Excuse me. So it kind of works through these. What if I wanted to test for whether or not these are independent events? Okay. So the literal definition of whether or not events are independent is if the conditional probability of an event is equal to the unconditional probability. So if I think about here, what this is saying is the conditional probability of O, right? I'm still looking for the probability of O. I've just conditioned on something else. So this is the conditional probability of O. If it was equal to the unconditional probability of O, so I'm not conditioning on anything, if they are equal to each other, we say they're independent. If they're not equal to each other, we would say they're not independent. So when we're asked whether or not these are independent events, this could be a possible answer, right? No, because the conditional and the unconditional probability are not the same. On the flip side, if we look at the rest of these answers, actually none of the other answers make sense. We actually don't even have to check to see if this is true, right? Because all these other possible answers, you need to be comparing the conditional probability of an event to the unconditional, right? So here I'm not even using the same events here, not using the same events here in my conditional, unconditional, and I'm not using the same here. So that none of those even make sense. Now a possible answer that could make sense, so I'll just write this here, is if we had something like this, right? If the conditional probability of an event is equal to the unconditional probability, if they are equal, then yes, those are independent, right? But in this one, we can actually rule all the answers out. But let's say this was the possible answer, and so we actually have to check to see if these things are equal, right? Or maybe to simplify, I'll put in here, just so it looks similar, right? So we're checking the same thing. And it doesn't matter which way we check it, right? If the conditional probability of LM is equal to the unconditional probability of LM, then the conditional probability of O will be equal to the unconditional, right? If LM is independent from O, O is independent from LM. So let's say this was the possible answer, and we actually have to check to see whether or not these two things are equal or not. Well, how can I find the conditional probability here? Well, actually, notice that's what we were looking for in the previous problem. I've already done that. If I want a conditional probability, I can just rewrite it as the intersection of those two things divided by what I'm conditioning on. So I've already found this from this earlier problem, right? So I found that it was 0.21. So the conditional probability was 0.21. If that's equal to the probability of O, the unconditional probability of O, they'd be independent. If they're not equal, they're not. So I go up here, what's the probability of being older than 55? 0.25. So sure enough, these two things aren't quite equal to each other. And so, where's my not equal to sign? There we go. So because they're not equal to each other, we would say they're not independent events. Final question in this set we have here is, are supporting national legalization of marijuana and being under the age of 55 mutually exclusive events? Well, if we look here at the possible answers, right, the actual definition, of being mutually exclusive is that the intersection is zero, or that these events can't happen at the same time. So this is where we had two circles that didn't overlap. So if we want mutually exclusive events, the only answers that make sense would be yes, they're mutually exclusive because the intersection is zero, or no, they're not because the intersection is not equal to zero. Now notice here, not even all of these represent intersections. These two actually represent the union of these events. So right away we know either A or D has to be correct, because to check for whether or not something's mutually exclusive, we're looking at the intersection. Now here this is a little bit more complicated because we said, being under the age of 55, so that's actually thinking about as O complement. But it doesn't, we're still checking for whether or not two events are mutually exclusive from each other. So when we're looking at the intersection of wanting marijuana legalized and being under 55, we say wanting marijuana legalized and being under 55, the intersection of those two events is 0.52. Well, that's not zero, right? So if that's not zero, they can't be mutually exclusive. The only way we could have mutually exclusive events is if we have a zero here in the contingency table. So the answer here would be no, because that intersection is not equal to zero. And up here, right, we had this one, we said it was no. Here, there are a correct answer for the independent question as well. So this is a set of questions that you're using this contingency table on to answer all 5 of these questions.